Imagine driving a vintage car at highway speeds through a construction zone filled with invisible obstacles. That's essentially what 3I-ATLAS is doing right now in the asteroid belt, except the car is 4 billion years old, the highway stretches across millions of kilometers, and a collision would erase the only samples of alien chemistry we've ever encountered. This interstellar visitor is writing its survival story in real time, each day bringing it deeper into the cosmic shooting gallery that lies between Mars and Jupiter. But here's what makes this encounter truly extraordinary. We're watching it happen. Stay until the end as we investigate whether this ancient giant can outlast the most dangerous crossing in our solar neighborhood, and what happens if it doesn't. By the way, if you enjoy drifting off to these cosmic explorations, feel free to subscribe or simply share your thoughts down in the comments. It helps others find their way here, too. But for now, let this interstellar journey carry you. And if you're ready, let's begin. Part 1. The Visitor from Beyond. On July 1st, 2025, in the dry mountains of Chile's Atacama Desert, a robot named Atlas was hunting for danger. The Asteroid Terrestrial Impact Last Alert System had been scanning the southern skies for years, cataloguing every rock that might one day threaten our world. But what it found that night was something else entirely. A faint speck of light, barely visible against the stellar backdrop of Sagittarius, moving with purpose through the darkness. Within 24 hours, NASA's finest minds had run the calculations. The numbers told a story that made astronomers around the world stop what they were doing and stare at their screens. This wasn't just another chunk of space debris. This was a messenger from the stars. They designated it 3I-ATLAS with the formal catalogue name C/2025N1, the 3I marking it as only the third confirmed interstellar visitor we've ever encountered. Think about that for a moment. In all of human history, we've watched billions of comets and asteroids circle our Sunday, but only 3 times have we caught something that doesn't belong to our solar family. What makes an object interstellar isn't just distance, it's mathematics. When our computers traced Atlas's path backward through space and time, they found an orbit so extreme it defied our solar system's gravitational architecture. Its eccentricity measured around 6.1. To put that in perspective, Earth's orbit has an eccentricity of 0.017, nearly a perfect circle. Even the most stretched comets from our own Oort cloud rarely exceed an eccentricity of 1. But Atlas? It was moving on what scientists call a strongly hyperbolic trajectory, approaching our Sun at speeds that could only mean one thing. It had traveled here from interstellar space. The velocity readings were staggering. Atlas was racing toward our Sun at approximately 60 kilometers per second, that's over 200,000 kilometers per hour. No gravitational slingshot from Jupiter or Saturn could accelerate a local object to such speeds. This visitor had been falling toward us across the galaxy for millions, perhaps billions of years. Its origin point made the discovery even more intriguing. When astronomers traced its trajectory backward, they found it arriving from the direction of Sagittarius, toward the central regions of our Milky Way galaxy. Not from the sparse outer reaches where our Sun resides, but from the crowded, ancient stellar neighborhoods closer to the galactic core. What stories might such a traveler carry? The safety question arose immediately, as it always does when the public hears about incoming space objects. But Atlas posed no threat to Earth. Its closest approach would occur in December 2025 at a comfortable distance of 1.8 astronomical units, about 270 million kilometers away. That's farther than Mars ever gets from Earth. We would be safe spectators to whatever unfolded, but the Sun was a different matter entirely. Atlas was on a collision course with our star's influence, scheduled to reach its closest point, called perihelion, around October 29th to 30th, 2025. At that moment, it would be just 1.36 to 1.4 astronomical units from the Sun's surface, well inside Mars's orbital path. For an interstellar visitor that had spent eons in the frozen darkness between stars, this encounter would be transformative. Already, telescopes were detecting the early signs of awakening. As Atlas drew closer to our Sun, the ancient ices locked within its nucleus began responding to stellar radiation. A faint coma, a cloud of gas and dust, was forming around the central body. The beginnings of a tail were becoming visible, like a ghost materializing in the cosmic void. The Gemini South Telescope captured detailed color imagery on August 27, 2025, revealing the subtle hues of sublimating materials. These weren't the familiar signatures of solar system comets. Something different was happening here, something that spoke to alien chemistry and formation conditions unlike anything in our local neighborhood. Estimating the size of Atlas proved challenging. Early observations suggested a nucleus anywhere from a few kilometers to 10 or 11 kilometers in diameter, larger than our first interstellar visitor, the cigar-shaped Oumuamua, but still small enough to fit comfortably within a terrestrial city. Yet size can be deceiving when dealing with objects whose surfaces and compositions remain mysterious. What we were witnessing was unprecedented, an interstellar comet awakening in real time as it encountered our Sun's influence. For the first time in human history, we could watch extraterrestrial materials, substances formed around alien stars, react to our local stellar environment. Every observation was a glimpse into chemistry and physics that had evolved in cosmic conditions completely foreign to our experience. This documentary exists because Atlas represents a once-in-a-lifetime opportunity. Unlike the quick flybys of previous interstellar visitors, this object was scheduled for a lengthy performance, spending months within range of our most powerful telescopes and spacecraft. We could study its composition, monitor its activity, and document its interaction with our solar environment in unprecedented detail. But there was something else about Atlas that made it special, something that would soon capture imaginations and generate controversy around the world. Its trajectory wasn't just interstellar, it was precisely aligned to thread through one of the most dangerous regions of our solar system. As Atlas raced toward its solar encounter, it would have to survive a gauntlet that has destroyed countless smaller objects throughout cosmic history. The asteroid belt was waiting. And for the first time we had a front row seat to watch an interstellar visitor attempt the crossing. Part 2. Origins and Hypotheses. Where does a traveler from the stars call home? For Atlas, the answer lies written in the mathematics of its motion, in the subtle clues encoded within its trajectory across our galaxy. When scientists traced its path backward through space and time, they found something remarkable. This wasn't just any random wanderer from the cosmic wilderness. The trajectory calculations pointed toward membership in what astronomers call the Milky Way's thick disk, an ancient stellar population that formed when our galaxy was young and turbulent. If this analysis holds true, Atlas could be extraordinarily old, possibly several billion years older than our entire solar system. Imagine, while our Sun was still a swirling cloud of gas and dust, Atlas may have already been wandering the galaxy as a frozen relic of cosmic antiquity. The thick disk represents our galaxy's middle age, a time when stellar formation was chaotic and metal, poor stars dominated the cosmic landscape. These are the stellar neighborhoods where planetary systems, if they formed at all, would have been very different from our own. Lower metallicity, different chemical abundances, alien formation conditions that could produce comets unlike anything in our local experience. But how does a comet become interstellar in the first place? The process is both violent and common throughout the galaxy. Every forming planetary system is a battleground of gravitational chaos. Giant planets migrate inward and outward, their massive gravitational fields flinging smaller objects into the void. Stellar encounters between neighboring stars can gravitationally strip entire comet populations from their parent systems. Close passes by massive objects can launch icy bodies on hyperbolic trajectories that carry them into interstellar space. Current models suggest that for every comet that remains bound to its parent star, dozens or hundreds are ejected into the galactic wilderness. Multiply this by the billions of planetary systems in our galaxy, and you begin to appreciate the scale of interstellar traffic flowing through cosmic space. Atlas isn't unique. it's one representative of a vast population of wandering worlds. Early attempts to measure Atlas's physical characteristics revealed intriguing constraints. Photometric observations suggested an upper size limit near 10 to 20 kilometers, making it significantly larger than our first interstellar visitor, Oumuamua, which measured only a few hundred meters in its longest dimension. Size matters in the comet business. Larger objects retain their volatile materials longer and can survive more extreme solar encounters. But it was the chemical analysis that truly set ATLAS apart from anything we'd seen before. When the James Webb Space Telescope turned its infrared eyes toward the growing coma, it detected something extraordinary, an unusually carbon dioxide-rich environment. The ratio of carbon dioxide to water vapor measured approximately 8:1, among the highest ratios ever observed in any comet. This chemical signature tells a story of formation conditions unlike those in our solar neighborhood. Carbon dioxide becomes the dominant ice only under very specific circumstances, either formation near the carbon dioxide ice line in a protoplanetary disk, or prolonged exposure to galactic cosmic radiation that can transform water ice into other compounds over millions of years. Both scenarios point to an origin story fundamentally different from local comets. Some researchers have speculated about ejection from a low metallicity red dwarf system versus a sun-like star. Red dwarfs dominate the thick disk population and have different planetary formation chemistry. Their habitable zones are closer to the star. Their protoplanetary disks may have different temperature and pressure gradients, and their lower ultraviolet output could preserve certain ice compositions over extended periods. Testing such hypotheses will require detailed spectroscopic analysis as ATLAS approaches the Sunday. The polarimetric studies added another layer of mystery. Early observations revealed unusual polarization behavior compared to typical solar system comets, suggesting differences in grain size, texture, or composition within the coma. These are the kinds of subtle clues that can reveal the internal structure and formation history of an object that has spent eons in the interstellar medium. Comparing ATLAS to our previous interstellar visitors highlights its uniqueness. 2I/Borisov, discovered in 2019, appeared remarkably similar to solar system comets in its composition and behavior, a familiar visitor from an alien system. Oumuamua, on the other hand, showed no clear cometary activity and exhibited a mysterious, non-gravitational acceleration that continues to generate scientific debate. Some recent hypotheses even suggest it could have been a fragment from a Pluto-sized object disrupted by stellar encounters. ATLAS seems to occupy middle ground, clearly cometary in its growing activity, but chemically distinct in ways that reveal its foreign origin. This combination makes it scientifically precious, familiar enough to understand, alien enough to teach us something new about planetary formation throughout the galaxy. What we still don't know could fill libraries. The precise nucleus size and shape remain uncertain, awaiting higher resolution observations as the comet brightens. Its rotation period and axis orientation are mysteries that will influence how uniformly or asymmetrically it sheds material. The detailed chemistry beyond carbon dioxide and water awaits more sensitive spectroscopy. Most critically, we don't know how its activity will evolve as solar heating intensifies. The next few months would bring unprecedented observational opportunities. The Hubble Space Telescope was already scheduling regular monitoring sessions. Ground-based 8 to 10 meter telescopes were coordinating campaigns to track compositional changes. Multiple spacecraft throughout the inner solar system were positioning themselves to observe from different vantage points. Each observation would be a first, the first detailed study of interstellar chemistry reacting to our Sun, the first real-time monitoring of alien materials under solar radiation, the first chance to compare directly the products of stellar formation in different galactic environments. ATLAS wasn't just a comet, it was a time capsule from the ancient galaxy, carrying samples of chemistry and physics from cosmic conditions we can barely imagine. But before we could decode all these secrets, Atlas would have to survive its journey through our solar system's most dangerous neighborhood. The asteroid belt was waiting, populated with millions of objects that had been quietly orbiting the Sun for 4.5 billion years. For an interstellar visitor racing through on a hyperbolic trajectory, that region represented a cosmic shooting gallery unlike anything it had encountered in its eons of wandering. The question wasn't just scientific curiosity anymore, it was survival. Part 3. The Asteroid Belt, a dangerous crossing. Between Mars and Jupiter lies a region that science fiction has painted as a cosmic minefield, millions of rocky fragments tumbling through space in chaotic orbits, waiting to pulverize any spacecraft foolish enough to venture into their domain. Hollywood loves the drama, heroes dodging asteroids at every turn, their ships barely escaping collision after collision through the cosmic debris field. The reality, as is often the case with space, is both more mundane and more fascinating than fiction suggests. The asteroid belt is indeed populated with millions of objects, ranging from dwarf planet-sized series down to countless smaller fragments and dust particles. But space, even in the most crowded regions of our solar system, remains overwhelmingly empty. Imagine Earth's orbit as a highway. The asteroid belt would be like a section of that highway where, instead of one car every few meters, you might encounter one car every several thousand kilometers. The average separation between significant asteroids is measured in millions of kilometers, distances that dwarf the size of the objects themselves. NASA's numerous missions through the belt have all crossed without incident, testament to the vastness of space even in its most populated regions. But ATLAS isn't taking the usual route. Most asteroids orbit the Sun in roughly the same direction as the planets, what astronomers call prograde motion. ATLAS, however, is traveling on a retrograde trajectory, inclined at approximately 175 degrees to the ecliptic plane. This means it's moving essentially backward relative to the belt's native population, creating relative velocities that are much higher than typical. Think of it as driving against traffic on a cosmic highway. While the risk of collision remains extremely small due to the vast distances involved, any encounter that does occur will be far more energetic than the gentle bumps between objects moving in similar directions. When objects collide at speeds of tens of kilometers per second, the results are spectacular and usually destructive. The belt itself is far from uniform. The densest concentrations lie near the ecliptic plane, the same geometric plane that contains Earth's orbit and most other planetary paths. Atlas's trajectory, despite its extreme inclination, passes very close to this plane, meaning it will slice directly through the belt's most populated layer rather than safely passing above or below it. The asteroid belt's residents are a diverse population. The largest objects, Ceres, Vesta, Pallas, and Hygeia, are massive enough to have retained spherical shapes and complex geological histories. Below them, thousands of irregular fragments represent the shattered remains of larger bodies, testimony to billions of years of collisional evolution. Many of these objects show compositional diversity that speaks to different formation conditions throughout the early solar system. There are the carbon-rich C-type asteroids, dark and primitive, preserving materials from the solar nebula's outer regions. The metallic S-types, likely fragments of differentiated bodies that once had molten cores. The rare M-types, almost pure metal, possibly the exposed cores of shattered planetoids. Some objects, dubbed immigrants by astronomers, clearly originated in the outer solar system before being scattered inward by planetary migration events. For ATLAS, racing through this cosmic museum at hyperbolic speeds, each object type represents a different flavor of potential interaction. But it's not the large, named asteroids that pose the greatest threat. It's the countless smaller fragments that occupy the size range from pebbles to boulders, too small to track individually but numerous enough to create a genuinely hazardous environment. The dust component deserves special attention. Micrometer to millimeter scale particles are abundant throughout the belt, continuously generated by collisions between larger objects and gradually spiraling inward toward the Sun due to radiation pressure. For a comet like ATLAS, developing an active coma and tail. This dust represents a sandblasting environment that could strip away material and alter the comet's appearance over time. Even more intriguingly, the dust interacts with the solar wind to create complex plasma effects. Charged grains feel electromagnetic forces in addition to gravity and radiation pressure, leading to instabilities and wave phenomena that could propagate throughout Atlas's growing coma. The physics becomes a three-body problem involving gravity, electromagnetism, and radiation, the kind of system that produces chaotic and unpredictable behavior. Yet, despite all these hazards, the overwhelming likelihood remains that Atlas will cross the belt without any significant encounters. NASA's assessment of collision probabilities consistently shows odds so small they're effectively negligible for any reasonably sized object. The belt is more like an ocean with rare islands than a crowded parking lot. Still, negligible isn't zero, and for an object carrying the scientific hopes of an entire astronomical community, even tiny risks deserve consideration. Micro-impacts could trigger localized outbursts, creating temporary changes in brightness or coma structure. Encounters with dust concentrations could create streaming effects in the tail, temporarily altering its appearance and providing information about the solar wind environment. Perhaps most importantly, the crossing itself represents a unique observational opportunity. Wide-field surveys can monitor Atlas continuously as it passes through different regions of the belt, watching for any changes in behavior that might indicate interactions with the local environment. Solar observing spacecraft can correlate tail disruptions with solar wind conditions, helping to distinguish between local interactions and heliospheric weather effects. The question facing astronomers wasn't really whether Atlas would survive. The odds strongly favored survival. The more interesting question was what we might learn from watching an interstellar object navigate our local debris field. Would we detect subtle changes in its activity as it encountered different dust environments? Could we use its passage to map previously unknown concentrations of small particles? Most intriguingly, how would Atlas's alien chemistry and structure respond to the unique conditions within the asteroid belt? This wasn't just about collision avoidance anymore. It was about using our own solar system as a laboratory to study materials from another stellar environment. As Atlas continued its approach, astronomers worldwide were preparing instruments and scheduling observations. The asteroid belt awaited, neither as dangerous as Hollywood imagined, nor as safe as statistics suggested, but as something more interesting than either extreme. A testing ground where an ancient wanderer would face its first real challenge since entering our solar system. The crossing had begun, and for the first time in human history, we were watching. Part 4. A tail forms, a warning sign. The transformation began subtly, almost imperceptibly, as Atlas drew closer to our Sunday. At first, the interstellar visitor appeared as nothing more than a point of light, indistinguishable from countless background stars, except for its slow drift against the celestial sphere. But as solar radiation intensified with each passing day, something remarkable began to happen. Deep within Atlas's ancient nucleus, ices that had remained frozen for eons started responding to stellar warmth. The process is deceptively simple in concept. Sunlight heats the surface, solid materials sublimate directly from ice to gas, and escaping vapors carry dust particles along to form a temporary atmosphere around the nucleus. This atmosphere, called a coma, can grow to dimensions larger than planets, transforming a small dirty snowball into one of the most spectacular sights in our solar system. But Atlas was revealing chemistry unlike anything astronomers had seen before. The James Webb Space Telescope's infrared observations showed that carbon dioxide dominated the early outgassing, creating a coma composition radically different from typical comets at similar solar distances. Most local comets begin their activity with water vapor as the primary constituent, with carbon dioxide becoming important only at much greater distances from the Sunday. The unusual chemistry wasn't just academically interesting, it was potentially diagnostic. Carbon dioxide sublimates at lower temperatures than water ice, meaning ATLAS was becoming active while still relatively far from the Sunday. This early activity could indicate either a surface composition dominated by volatile ices or internal heating from some other source. Neither possibility matched the behavior patterns of solar system comets. As the coma expanded, solar radiation began sculpting it into more complex structures. Photons carry momentum, and when they scatter off dust particles, they impart a gentle but persistent push away from the Sunday. Simultaneously, the solar wind, a stream of charged particles flowing outward from our star, ionizes some of the gas molecules and sweeps them away through magnetic field interactions. These two processes create the characteristic dual-tail structure that makes comets so visually stunning. The dust tail, composed of solid particles reflecting sunlight, curves gracefully away from the Sun along the comet's orbital path. The plasma tail, made of ionized gases, points directly away from the Sun regardless of the comet's motion, creating streamers that can extend for millions of kilometers through space. For ATLAS, the growing tail represented both beauty and vulnerability. Each particle lost to the solar wind or radiation pressure was material that had survived the interstellar journey, only to be stripped away during its brief encounter with our Sunday. The tail was simultaneously a triumph, proof that ancient interstellar ices were responding to our local star, and a countdown timer, marking the gradual erosion of irreplaceable scientific samples. The plasma component of the tail introduced additional complications. When solar wind particles encounter cometary ions, they transfer energy and momentum through electromagnetic interactions. This mass loading can deflect the solar wind flow, creating magnetic field enhancements and wave structures that propagate both upstream and downstream from the comet. The effect transforms the comet into a kind of cosmic weather station, its plasma tail responding sensitively to variations in solar wind density, velocity, and magnetic field strength. During periods of intense solar activity, coronal mass ejections or high-speed stream interactions, the plasma tail can be dramatically kinked, disconnected, or even temporarily destroyed, only to reform as conditions stabilize. ATLAS's unusual chemistry made these interactions particularly intriguing. Carbon dioxide ions behave differently from water vapor ions in plasma environments, potentially creating new types of instabilities or wave phenomena that hadn't been observed in previous comets. The growing tail wasn't just a pretty sight, it was a laboratory for studying plasma physics under conditions impossible to recreate on Earth. But there was something troubling about the tail's development that made some astronomers nervous. The asymmetric nature of the early outgassing suggested that activity wasn't uniformly distributed across the nucleus surface. This could indicate exposed volatile patches, structural weaknesses, or internal composition variations that might become important as solar heating intensified. Asymmetric outgassing creates torques that can alter a comet's rotation, potentially leading to tumbling motions or even structural failure in extreme cases. The growing brightness and expanding coma were beautiful to observe, but they also represented increasing stress on a nucleus that had already survived eons of cosmic ray bombardment and thermal cycling during its interstellar journey. The observational data was painting a picture of an object under increasing strain. Brightness curves showed irregular variations that suggested discrete outburst events rather than smooth, continuous activity. High-resolution imaging revealed jet-like features in the coma, indicating localized sources of gas and dust emission. The overall morphology was becoming more complex and dynamic as ATLAS approached its solar encounter. Each of these signs individually might be considered normal comet behavior, but collectively, they suggested an object that was responding more dramatically to solar heating than typical comets at similar distances. Whether this represented the natural behavior of interstellar materials or a warning sign of impending structural problems remained unclear. The timing couldn't have been worse. ATLAS was still approaching the asteroid belt, the most hazardous phase of its journey through our solar system. A comet showing signs of instability or irregular activity would be particularly vulnerable to the additional stresses of navigating through the belt's dust environment and gravitational perturbations. Yet the growing activity also represented unprecedented scientific opportunity. Every spectral line, every brightness variation, every morphological change in the coma and tail was providing new information about interstellar materials and their interaction with our local stellar environment. The warning signs that worried some astronomers were the very phenomena that made ATLAS scientifically priceless. As telescopes around the world tracked the developing tail, a more fundamental question began emerging. Was ATLAS behaving like a typical comet from an alien system, or was there something more unusual about this particular visitor? The chemical signatures were already proving alien. The activity patterns were showing unexpected characteristics, and ahead lay the most dangerous part of its journey. The asteroid belt was no longer just a navigational hazard. It was becoming a test that might determine whether this ancient wanderer would survive long enough to reveal all its secrets. The tale that marked Atlas's awakening also marked the beginning of its greatest vulnerability. Something was stirring in the cosmic depths, and we were about to find out what an interstellar visitor was really made of. Part 5. Historical Parallels. Other Visitors. ATLAS wasn't the first messenger from beyond our solar system to grace our telescopes, and the stories of its predecessors offer both hope and caution for what might unfold in the months ahead. Each interstellar visitor has carried its own mysteries, its own surprises, and its own lessons about the diversity of objects wandering through our galactic neighborhood. The first confirmed interstellar object, designated 1I/Oumuamua, burst into public consciousness in October 2017 when the Pan-STARRS telescope detected it racing through the inner solar system. Hawaiian astronomers gave it a name meaning messenger from afar arriving first, prophetic words that captured both its significance and its mystery. Oumuamua defied every expectation. Its extreme elongation, roughly 10 times longer than it was wide, suggested either a highly unusual natural formation or, as some speculated, something artificial. More puzzling still was its lack of any detectable coma or tail, despite passing well within Earth's orbit. This wasn't behaving like any comet astronomers had ever observed. Then came the acceleration anomaly. As telescopes tracked Oumuamua's departure, they detected a small but persistent non-gravitational acceleration that couldn't be explained by solar radiation pressure alone. The object was speeding up in ways that suggested outgassing, yet no gas or dust emissions were visible. The mystery deepened when researchers calculated that the acceleration was roughly consistent with water vapor sublimation, but at levels too low to detect with existing instruments. Recent hypotheses have attempted to resolve Oumuamua's contradictions. One intriguing proposal suggests it might be a fragment from a Pluto-sized object that was disrupted by a stellar encounter, explaining both its unusual shape and its apparently non-cometary composition. Another theory invokes hydrogen ice, formed during the object's long journey through interstellar space, which could sublimate invisibly while still providing the observed acceleration. The second confirmed interstellar visitor, 2Y/Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov, presented a completely different personality. This object looked and behaved exactly like astronomers expected an interstellar comet should: a healthy coma, a developing tail, and spectroscopic signatures that closely matched solar system comets. Borisov was, in many ways, reassuringly normal, a familiar type of object from an alien stellar system. Detailed observations of Borisov revealed water vapor, carbon monoxide, and various hydrocarbons in ratios similar to comets from our own Oort cloud. Its nucleus appeared intact throughout its solar encounter, and its activity patterns followed predictable curves based on solar heating models. If Oumuamua was the strange cousin, Borisov was the well-behaved family member who confirmed that other stellar systems produce objects fundamentally similar to our own. But ATLAS seems to occupy a middle ground between these extremes, sharing characteristics with each while displaying unique properties of its own. Like Borisov, it's clearly cometary, developing the expected coma and tail as it approaches the Sunday. Like Oumuamua, it's revealing chemical and physical properties that challenge our understanding of typical comet behavior. The trajectory comparisons are particularly striking. Oumuamua entered our solar system at a steep angle to the ecliptic plane and departed without coming close to any major gravitational sources. Borisov followed a more moderate path that brought it relatively close to the Sun but avoided the most densely populated regions of our system. ATLAS, with its near-ecliptic retrograde trajectory, is taking the most dramatic route of all, threading directly through the asteroid belt on its way to solar encounter. For additional perspective, consider the recent spectacular performance of Comet C/2023 A3, Tsuchinshan ATLAS, which captivated observers throughout 2024. This solar system comet provided a masterclass in cometary behavior, developing magnificent tails and surviving close solar passage intact. Its interactions with coronal mass ejections were documented in detail by the SOHO spacecraft, showing how solar activity can dramatically restructure comet tails through magnetic reconnection events. These observations are relevant because they demonstrate that comets regularly experience tail disconnections and reformations without suffering permanent damage. The Solar and Heliospheric Observatory has documented hundreds of such events, showing that dramatic tail disruptions are part of normal comet physics, rather than signs of impending destruction. This precedent suggests that ATLAS might survive even spectacular interactions with solar wind disturbances. However, there's an important distinction to emphasize. While comets often trigger dramatic tail effects when they encounter solar wind structures, there's no credible evidence that comets themselves trigger major solar events. The correlation between comet passages and solar activity remains a subject of speculation rather than established science, despite persistent claims in some circles. What makes ATLAS scientifically more valuable than previous interstellar visitors is its chemistry. While Borisov resembled local comets and Oumuamua showed no clear compositional signatures, ATLAS is providing detailed spectroscopic data that reveals genuinely alien material properties. The carbon dioxide-dominated coma represents chemistry that doesn't exist among well-studied solar system comets, offering insights into formation conditions around different types of stars. The observational advantages are also unprecedented. Oumuamua was discovered when it was already departing, leaving only a few months for detailed study. Borisov provided a longer observational window but remained relatively faint throughout its passage. ATLAS is being tracked from great distances with multiple years of potential observations, allowing astronomers to document its evolution through various phases of solar interaction. Coordination among observatories has also improved dramatically since the previous interstellar visits. NASA, ESA, NOILAB, and numerous international facilities are sharing data in near real time, ensuring that critical observations aren't missed due to weather, technical problems, or scheduling conflicts at individual sites. Amateur astronomers are also contributing, providing continuous monitoring that professional telescopes can't match. The data processing and analysis capabilities have similarly advanced. Machine learning algorithms can now identify subtle changes in comet morphology that might have been missed in earlier observations. Improved spectroscopic techniques can detect trace species at much lower concentrations than previously possible. Computer models can simulate complex plasma interactions and dust dynamics with unprecedented detail. Yet for all these advantages, ATLAS faces challenges that its predecessors avoided. Neither Oumuamua nor Borisov had to navigate through the asteroid belt's dust environment while developing active comae and tails. Neither encountered the complex gravitational and electromagnetic interactions that await ATLAS as it threads through the solar system's most crowded region. The historical precedents offer both encouragement and caution. They demonstrate that interstellar objects can survive solar system passage intact, but they also show that each visitor brings its own unique properties and behaviors. ATLAS may follow patterns established by its predecessors, or it may surprise us with entirely new phenomena. As we prepared to witness Atlas's passage through the asteroid belt, the experiences with previous interstellar visitors provided context but no guarantees. Each cosmic messenger writes its own story across our skies, and Atlas was about to begin the most dangerous chapter of its billion-year journey. The belt awaited, and with it, the answers to questions that had been traveling toward us since before our species existed. Part 6. Trajectory: Cutting Through the Meat of the Belt. Understanding Atlas's path through our solar system requires thinking in 3 dimensions, with orbital mechanics that would challenge even experienced spacecraft navigators. Most objects in our cosmic neighborhood travel in roughly the same direction as the planets, a stately procession that preserves the angular momentum from our solar system's formation. But Atlas is different. It's traveling backward. The technical term is retrograde motion, and Atlas's orbital inclination of approximately 175 degrees means it's moving almost exactly opposite to the normal traffic flow. Imagine every car on a highway traveling east, while one vehicle races westbound in the passing lane. That's essentially what Atlas is doing on a cosmic scale, creating relative velocities far higher than anything typical for our solar neighborhood. This retrograde trajectory isn't just unusual, it's potentially dangerous. When objects collide in space, the kinetic energy involved depends on the square of their relative velocity. A head-on collision between objects moving in opposite directions releases far more energy than a gentle rear-end encounter between objects traveling the same way. For Atlas, threading through the asteroid belt against the traffic flow means that any collision, however unlikely, would be catastrophically energetic. The geometry of its approach is equally dramatic. Atlas entered the observable region of our solar system from the direction of Sagittarius, initially appearing as a faint magnitude 16 to 18 object barely detectable by professional telescopes. As it races inward from approximately 3 to 5 astronomical units in July, it will cross the asteroid belt's main zone and reach its closest solar approach of 1.357 astronomical units by late October 2025. For observers trying to track this cosmic visitor, the sky path presents its own challenges. During July and August, Atlas remained in the constellation regions of Sagittarius and Ophiuchus, faint enough to require large telescopes and careful tracking to follow its motion. As it brightens with increasing activity, smaller telescopes will eventually be able to observe it, but the rapidly changing position makes continuous observation challenging. The trajectory brings Atlas tantalizingly close to several planets, though close in astronomical terms still means millions of kilometers. On October 3, 2025, it will pass approximately 0.19 astronomical units from Mars, roughly 28 million kilometers. While this isn't anywhere near collision distance, it's close enough that some Mars-orbiting spacecraft might be able to observe the comet from a unique vantage point. Later encounters include a passage 0.65 astronomical units from Venus on November 3rd and a more distant 0.36 astronomical units from Jupiter on March 16, 2026. These planetary encounters won't significantly alter Atlas's trajectory. Its hyperbolic orbit carries too much energy for gravitational capture, but they provide excellent opportunities for triangulation and parallax measurements from multiple spacecraft locations. The Earth clearance remains safely large throughout the encounter. The closest approach occurs in December 2025 at approximately 1.8 astronomical units, about 270 million kilometers. This is farther than Mars ever gets from Earth, eliminating any possibility of direct threat to our planet. Even if Atlas were to fragment completely, the debris would follow the same hyperbolic trajectory and miss Earth entirely. The speed numbers are staggering in their own right. Atlas's hyperbolic excess velocity, the speed it would have in interstellar space, far from any gravitational influence, measures approximately 58 kilometers per second in some analyses. As it falls toward the Sun, gravitational acceleration increases this to even higher values, creating relative velocities with asteroid belt objects that can exceed 100 kilometers per second. To put this in perspective, the fastest human-made objects, like the Parker Solar Probe, at its closest solar approach, reach speeds around 190 kilometers per second. ATLAS is traveling at a significant fraction of the highest speeds we can achieve with our most advanced propulsion technology, but it's been maintaining this pace for millions or billions of years. The near-ecliptic retrograde path creates maximum interaction with the solar wind structures that are most common in the ecliptic plane. This isn't coincidental. The ecliptic plane contains not just the highest density of solid objects, but also the most complex electromagnetic environment. Coronal mass ejections, co-rotating interaction regions, and other solar wind features tend to be most pronounced near the solar equatorial plane, which approximately aligns with the ecliptic. For heliophysics researchers, ATLAS's trajectory provides an unprecedented opportunity to study how an active comet interacts with various solar wind structures as it crosses different heliospheric regions. Multiple spacecraft positioned throughout the inner solar system can observe the same comet from different angles simultaneously, providing stereo observations that reveal three-dimensional structure in ways impossible from Earth-based telescopes alone. The trajectory also maximizes the observational window for ground-based telescopes. Unlike previous interstellar visitors that approached from high inclinations and provided only brief viewing opportunities, ATLAS remains visible from Earth for many months. This extended timeline allows for seasonal observations from different hemispheres, weather backup at multiple observatories, and the luxury of repeated measurements to confirm unusual findings. What makes this path particularly scientifically valuable is that ATLAS will sample multiple distinct environments during its solar system passage. The outer asteroid belt region, where it spent July and August, represents a relatively pristine environment with minimal solar wind interaction. The main belt zone, which it entered in September, provides intermediate conditions with moderate solar heating and complex dust interactions. The inner system, where it will spend October and November, offers maximum solar wind coupling and intense radiation environments. Each of these regions will test different aspects of ATLAS's structure and composition. The outer belt transit revealed its baseline activity level and chemical signatures. The main belt passage will show how it responds to dust interactions and gravitational perturbations from larger asteroids. The inner system encounter will demonstrate whether its nucleus can withstand extreme solar heating while maintaining structural integrity. The retrograde nature of the orbit creates one additional advantage for observers. The relative motion against the stellar background is maximized, making it easier to distinguish the comet from background stars and to measure its position precisely. This helps with both tracking accuracy and contamination rejection in spectroscopic observations. As ATLAS races toward its October perihelion, every day brings it deeper into the asteroid belt's most populated regions. The trajectory that makes it scientifically valuable also makes it vulnerable to the kinds of interactions that have destroyed smaller objects throughout solar system history. The path through the belt isn't just a route, it's a gauntlet that will test everything about this ancient wanderer's ability to survive in our cosmic neighborhood. The mathematics of orbital mechanics had delivered us a perfect natural experiment, an interstellar object following a trajectory designed to maximize both scientific opportunity and dramatic tension. ATLAS was threading the needle through our solar system's most dangerous region, and we had front-row seats to watch what happened next. Part 7. Collision Scenarios. The asteroid belt contains some of the most famous names in our solar system: Ceres, Vesta, Pallas, Hygeia, massive worlds in their own right that dwarf most of the objects humans have visited. Ceres alone measures nearly 1,000 kilometers across, large enough to have achieved hydrostatic equilibrium and earn classification as a dwarf planet. Vesta, with its distinctive shape and ancient impact basins, represents the battered remnant of what was once a much larger world. These are the titans of the belt, the gravitational anchors around which smaller debris has organized itself over billions of years. For ATLAS, racing through this region at hyperbolic speeds, even these massive objects pose essentially no direct threat. Space is unimaginably large compared to the size of the objects within it, and the probability calculations are reassuring in their astronomical improbability. To visualize the scale, if Earth were a marble sitting in New York City, the nearest asteroid belt object might be another marble located somewhere in Los Angeles. The intervening space is simply empty. NASA's assessment of collision probabilities consistently shows odds so remote they barely deserve consideration. Every spacecraft that has crossed the asteroid belt, from Pioneer 10 in 1973 to the most recent Mars missions, has done so without encountering anything larger than microscopic dust particles. The belt's reputation as a cosmic shooting gallery is more Hollywood fiction than physical reality. But ATLAS isn't following the same predictable paths as human spacecraft. Its retrograde trajectory means it's essentially driving against traffic on the cosmic interstate, creating relative velocities that can exceed 100 kilometers per second during chance encounters. While the probability of collision remains infinitesimally small, the energy involved in any such encounter would be catastrophic. Consider what happens when objects collide at these velocities. The kinetic energy scales with the square of the relative speed, meaning that a retrograde collision releases roughly 4 times more energy than the same encounter between objects moving in the same direction. At 100 kilometers per second, even a small rocky fragment carries the destructive power of a nuclear weapon. A direct hit from anything larger than a pebble would likely shatter Atlas's nucleus completely. The thought experiment is both fascinating and terrifying. If ATLAS were to encounter a significant asteroid fragment, the collision would create a brief, brilliant flash visible from Earth-based telescopes. The nucleus would disintegrate into a cloud of smaller fragments, each following its own hyperbolic trajectory out of the solar system. Within hours or days, what had been a single interstellar visitor would become a scattered swarm of debris, impossible to track individually, and carrying away forever the secrets of its alien chemistry. Such an event would trigger immediate concerns about Earth's safety, despite the mathematical impossibility of any threat. Public imagination inevitably turns to worst-case scenarios when cosmic collisions make headlines. Could fragments be redirected toward Earth? Could a gravitational encounter with Jupiter or Mars send debris on an Earth-crossing path? The orbital mechanics provide clear answers: no. Atlas's hyperbolic trajectory carries far too much energy for gravitational deflection by any solar system object. Even a close encounter with Jupiter, by far our most massive planet, couldn't bend Atlas's path enough to threaten Earth. The fragments from any collision would continue on hyperbolic trajectories, racing out of the solar system and back into interstellar space. More realistically, the true collision hazard for ATLAS comes not from the named asteroids but from the countless smaller objects that populate the belt. Fragments ranging from centimeters to meters in diameter are numerous enough to create a genuinely hazardous environment for any object with a large cross-sectional area. And as ATLAS develops its coma and tail, its effective size grows from a few kilometers to potentially hundreds of thousands of kilometers. The coma represents a particular vulnerability. While the nucleus itself is solid and relatively compact, the surrounding gas and dust cloud is tenuous and extended. Small particles striking the coma won't destroy ATLAS, but they could disrupt the delicate structures within the tail or trigger localized outbursts that change the comet's appearance dramatically. These micro-collision effects might actually be observable from Earth. Sudden brightness spikes, asymmetric jets, or changes in tail morphology could all indicate interactions with belt material. Such events would provide unique insights into both Atlas's internal structure and the previously unmapped small particle population within the asteroid belt. The gravitational effects of large asteroids present a different kind of hazard. While direct collision with Ceres or Vesta is essentially impossible, gravitational encounters could still influence Atlas's trajectory in subtle ways. These perturbations wouldn't redirect the comet toward Earth, but they might alter its spin rate, change the orientation of its rotation axis, or stress internal structures in ways that promote fragmentation. Perhaps most intriguingly, the asteroid belt contains its own population of immigrants. objects that clearly formed elsewhere in the solar system before being scattered into their current orbits by planetary migration events. Some of these displaced objects might share compositional similarities with ATLAS, having originated in the outer solar system where carbon dioxide ices are more common. An encounter with such an immigrant could provide fascinating comparative data about formation conditions throughout our stellar neighborhood. The Mars encounter on October 3rd deserves special attention in this context. At 0.19 astronomical units, ATLAS will pass close enough for detailed observation by Mars-orbiting spacecraft, but far enough to avoid any gravitational complications. This represents an ideal compromise, scientifically valuable proximity without the risks associated with closer encounters. For the broader question of belt navigation, the survival statistics strongly favor ATLAS completing its passage intact. The overwhelming likelihood is that it will thread through the most dangerous region of our solar system without encountering anything more substantial than microscopic dust. The belt may look crowded in artistic renderings, but the reality of celestial mechanics makes survival the overwhelmingly probable outcome. Yet, the non-zero probability of collision adds dramatic tension to every observation. Each day that passes without incident increases confidence in ATLAS's ultimate survival, while each unusual brightness variation or morphological change raises questions about possible interactions with unseen belt material. The collision scenarios, however unlikely, remind us that space remains a fundamentally hazardous environment where high-energy encounters can erase billion-year journeys in milliseconds. ATLAS has already survived eons of interstellar travel, cosmic ray bombardment, and gravitational encounters with unknown objects in the galactic disk. The irony would be overwhelming if it were to be destroyed by debris from our own solar system's formation. But as each day passed without catastrophe, confidence grew that ATLAS would emerge from the belt intact, carrying its cargo of alien chemistry toward the ultimate test of solar encounter. The collision scenarios remained possible, but survival was becoming probable, and survival meant answers to questions that had been traveling toward us since before our sun was born. Part 8. The Plasma Factor. As ATLAS develops its growing coma and tail, it's transforming from a simple rocky nucleus into something far more complex and dynamic, a massive plasma laboratory conducting experiments that would be impossible to replicate on Earth. The physics at work here involves the fundamental interactions between matter, electromagnetic fields, and radiation that govern much of the behavior we observe throughout the universe. The process begins when solar ultraviolet radiation ionizes some of the neutral gas molecules escaping from ATLAS's nucleus. Carbon dioxide and water vapor, the primary components of its coma, lose electrons and become positively charged ions floating in a sea of free electrons. This ionized gas, plasma, behaves very differently from ordinary matter, responding to magnetic and electric fields in ways that can seem almost alive. The solar wind, that invisible stream of charged particles flowing outward from our sun at speeds of several hundred kilometers per second, doesn't simply flow around objects like a river around rocks. When it encounters the ionized coma of a comet like ATLAS, something remarkable happens. The plasma environments begin talking to each other through electromagnetic interactions. Fresh cometary ions get picked up by the solar wind's magnetic field and accelerated to high speeds, creating what plasma physicists call mass loading. This process is somewhat like adding sandbags to a fast-moving river. The additional mass slows down the flow and changes its direction. For ATLAS, the effect is even more pronounced because of its unusual chemistry. Carbon dioxide ions have different mass and charge properties than the water vapor ions that dominate most comet studies, potentially creating plasma behaviors that haven't been observed before. The European Space Agency's Rosetta mission provided detailed observations of mass loading effects at comet 67P/Churyumov-Gerasimenko, documenting deflections of the solar wind by more than 45 degrees when the comet was active. The solar wind, which normally flows radially outward from the sun, gets bent and twisted into complex patterns around the comet, creating magnetic field enhancements and wave structures that propagate both upstream and downstream. These electromagnetic interactions generate waves, magnetosonic waves, alpha waves, and other exotic oscillations that carry energy and information through the plasma environment. The waves can travel faster than the bulk motion of the plasma itself, providing a kind of early warning system that announces the comet's presence to the solar wind before the physical material arrives. For ATLAS, racing through the asteroid belt on its retrograde trajectory, these plasma interactions take on additional complexity. The high relative velocities mean that encounters with the solar wind are more energetic than typical, potentially generating stronger wave signatures and more dramatic deflection effects. The near-ecliptic path ensures maximum interaction with the solar wind structures that are most common in the solar equatorial plane. The tail itself becomes a kind of cosmic windsock, its structure revealing information about solar wind conditions that can't be measured directly from Earth. When coronal mass ejections or high-speed stream interactions create disturbances in the solar wind, the plasma tail responds almost immediately. Magnetic reconnection events can literally disconnect sections of the tail, which then drift away while new plasma structures reform closer to the nucleus. These tail disconnection events have been observed in numerous comets, creating some of the most dramatic time-lapse sequences in astronomical photography. The plasma tail appears to be yanked away by invisible forces, writhing and twisting as it interacts with changing magnetic field conditions. Within hours or days, a new tail reforms, only to potentially suffer the same fate when the next solar wind disturbance arrives. ATLAS's unusual carbon dioxide-dominated chemistry could make these interactions particularly spectacular. Carbon dioxide ions have different gyroradii, the characteristic spiral patterns they follow in magnetic fields, compared to water vapor ions. This means the plasma tail might develop structures and instabilities that haven't been observed in previous comets, providing new insights into plasma physics under extreme conditions. The charging environment around ATLAS adds another layer of complexity. Dust particles in the coma acquire electric charges through interactions with solar ultraviolet radiation, plasma currents, and secondary electron emission. These charged grains then respond to both electric and magnetic forces in addition to gravity and radiation pressure, creating dust dynamics that can be chaotic and unpredictable. Laboratory experiments with dusty plasmas have revealed instabilities, wave phenomena, and collective behaviors that emerge when charged particles interact through long-range electromagnetic forces. In the environment around ATLAS, these effects operate on scales from micrometers to millions of kilometers, creating a natural laboratory for studying phenomena that bridge atomic physics and astrophysics. The solar wind conditions that ATLAS will encounter during its belt passage are particularly interesting from a heliophysics perspective. The ecliptic plane contains the most complex magnetic field structures, including sector boundaries where the solar magnetic field changes polarity, co-rotating interaction regions where fast solar wind catches up with slow wind, and the occasional passage of coronal mass ejections. Each of these structures will test different aspects of ATLAS's plasma environment. Sector boundary crossings can trigger sudden changes in tail morphology. Co-rotating interaction regions can compress the coma and enhance wave generation. Coronal mass ejections can completely reconfigure the magnetic field topology, potentially disconnecting the tail multiple times as the disturbance passes. Multiple spacecraft throughout the inner solar system are positioned to observe these interactions from different vantage points. The Solar and Heliospheric Observatory, the Solar Dynamics Observatory, the Parker Solar Probe, and various Mars-orbiting missions can provide simultaneous measurements of solar wind conditions and ATLAS's response, creating three-dimensional maps of plasma interactions that would be impossible from Earth-based observations alone. The data from these plasma interactions will have implications far beyond cometary science. Understanding how ionized gases behave under extreme conditions provides insights into stellar atmospheres, planetary magnetospheres, and the interstellar medium itself. ATLAS is serving as a natural probe of plasma physics processes that operate throughout the universe. Perhaps most remarkably, the plasma environment around ATLAS is helping to create the very structures that make it visible from Earth. The ionized tail carries away not just individual atoms and molecules, but also the electromagnetic signatures of its alien chemistry. Every spectral line, every polarization measurement, every brightness variation carries information about materials formed around another star, now interacting with our local plasma environment. As ATLAS continues deeper into the asteroid belt, these plasma interactions will intensify. The growing coma will provide more material for ionization. The increasing solar radiation will drive stronger chemical processes. The complex magnetic field environment of the inner solar system will create more opportunities for dramatic tail interactions. The plasma factor wasn't just a scientific curiosity, it was becoming central to ATLAS's survival prospects. The electromagnetic forces at work in its coma and tail could either help stabilize the nucleus against fragmentation or contribute to internal stresses that promote breakup. The answer would depend on details of plasma physics that we were only beginning to understand. One thing was certain: ATLAS was no longer just a comet. It had become a plasma laboratory, conducting experiments in fundamental physics while racing through the most dangerous region of our solar system. The results of those experiments would determine not just what we learned about interstellar chemistry, but whether the ancient wanderer would survive long enough to reveal all its secrets. Part 9. Hidden Dangers, Dust and Mini Collisions. While astronomers focus on the dramatic possibility of ATLAS colliding with a large asteroid, the real hazards lurking in the belt are far more subtle and perhaps more dangerous. The space between Mars and Jupiter isn't empty. It's filled with countless particles ranging from microscopic dust grains to pebble-sized fragments, all moving at various speeds and creating a sandblasting environment that could slowly erode away the very secrets we're hoping to uncover. These micro-impacts operate on a completely different scale than catastrophic collisions, but their cumulative effect can be just as destructive over time. Every dust grain that strikes ATLAS's nucleus carries kinetic energy proportional to the square of its velocity. At typical belt crossing speeds, even microscopic particles hit with the force of tiny bullets, gradually sputtering away surface material and potentially exposing fresh layers beneath. The process is called space weathering, and it's been shaping objects throughout our solar system for billions of years. On airless bodies like asteroids and moons, constant bombardment by cosmic dust gradually darkens surfaces, creates microscopic glass spheres, and alters chemical signatures in ways that can mask the original composition. For ATLAS, carrying precious samples of interstellar chemistry, this erosive process could be destroying evidence faster than we can analyze it. But erosion might also work in our favor. If ATLAS developed a radiation-darkened crust during its billions of years in interstellar space, micro-impacts could expose fresher material beneath, revealing chemical signatures that would otherwise remain hidden. Some of the brightness variations and jets that telescopes are observing might result from exactly this process. Small impacts exposing volatile rich layers that then sublimate rapidly when heated by sunlight. The thermal stress environment adds another layer of complexity. As ATLAS approaches the Sun, its surface temperature rises dramatically, causing expansion of the outer layers while the interior remains cold. These thermal gradients create mechanical stresses that can crack even solid rock, opening fissures that allow internal volatiles to escape. The result is often the explosive jets and outbursts that make comet watching so unpredictable. Historical precedents suggest caution. Comet C/2019Y4, also named ATLAS, began brightening dramatically in early 2020, raising hopes for a spectacular naked-eye display. Instead, high-resolution observations revealed that the nucleus was fragmenting, breaking apart into dozens of smaller pieces that gradually faded as they dispersed. The breakup wasn't caused by any single catastrophic event, but rather by the accumulated stresses of solar heating acting on an object that was already structurally compromised. Comet Ison provides another cautionary tale. This promising sun grazer developed a beautiful tail and generated enormous public excitement as it approached the sun in 2013. But as it neared perihelion, tidal forces and intense solar heating overwhelmed its structural integrity. Ison essentially evaporated, leaving behind only a cloud of debris that quickly dispersed into space. The question for 3I-ATLAS is whether its unusual composition makes it more or less susceptible to these destructive processes. The carbon dioxide-rich chemistry detected by the James Webb Space Telescope could indicate either a tougher, more radiation-processed crust or a more volatile, fragile interior. Both scenarios have precedence among solar system comets, but neither provides clear guidance for predicting the behavior of an interstellar visitor. Age might be Atlas's enemy or its ally. If the object is indeed several billion years older than our solar system, it has survived cosmic ray bombardment and thermal cycling that would destroy less robust objects. This extended survival might indicate unusual structural strength or compositional stability. Alternatively, the same processes that enabled its survival might have left it brittle and prone to catastrophic failure under the intense heating of solar approach. The observational signatures of internal stress are becoming increasingly apparent as Atlas brightens. Sudden changes in brightness, asymmetric jets, and irregular variations in coma density all suggest that material is being released episodically rather than smoothly. These outbursts could represent the opening of new vents as thermal expansion cracks the surface, or they could indicate the beginning of structural failure. High-resolution imaging campaigns are watching for the telltale signs of fragmentation, multiple condensations within the coma, elongation of the central brightness distribution, or the appearance of separate nuclei following independent trajectories. The Hubble Space Telescope and ground-based adaptive optics systems can resolve features smaller than the nucleus itself, providing early warning of any developing instabilities. The asteroid belt's dust environment adds an external stress to these internal processes. While individual dust impacts are tiny, their collective effect over months of belt passage could be significant. The growing coma around Atlas presents a large cross-sectional area for dust encounters, and high-speed impacts could trigger localized heating that initiates new outgassing events. Particularly intriguing is the possibility that belt dust could interact with Atlas's unusual chemistry in unexpected ways. Most studies of dust impacts assume water-ice-dominated compositions typical of solar system comets. But carbon dioxide behaves differently under impact heating, subliming at lower temperatures and potentially creating more explosive responses to external disturbances. The dust bands and zodiacal cloud that fill the inner solar system could create additional complications. These structures, formed by dust spiraling inward from asteroid collisions, create a background environment of particle impacts that varies with location and time. As Atlas crosses different dust density regions, its brightness and tail morphology might change in ways that reveal information about both the comet's properties and the previously unmapped dust environment. One positive aspect of potential dust encounters is their scientific value. Even destructive impacts would expand our sample of interstellar materials, dispersing previously hidden interior composition throughout the coma, where telescopes could analyze it spectroscopically. In some sense, the asteroid belt dust might act as a natural drill, boring samples from Atlas's interior and making them available for remote analysis. The timing of these potential interactions is crucial. Each week that Atlas survives intact increases the scientific return from the mission, allowing more sophisticated measurements and longer-term monitoring of compositional changes. But each week also brings deeper penetration into the belt's most populated regions, increasing the probability of encounters with larger particles that could trigger more dramatic responses. Perhaps most importantly, the dust and mini-collision environment represents a test that no other interstellar visitor has faced. Neither Oumuamua nor Borisov developed significant comae while passing through dense particle environments. Atlas is pioneering new territory, both literally and figuratively, as the first active interstellar comet to navigate the asteroid belt's hazardous dust storms. The outcome would depend on factors we were only beginning to understand: the precise balance between Atlas's structural strength and the cumulative stresses of belt passage, the interaction between its unusual chemistry and the dust impact environment, and the internal composition gradients that determine how the object responds to external disturbances. Every observation was now critical. Every brightness measurement potentially the last clear look at an intact interstellar nucleus. The hidden dangers of dust and mini-collisions weren't as dramatic as catastrophic asteroid impacts, but they might prove just as decisive in determining whether Atlas would survive to reveal its secrets, or gradually disintegrate under the accumulated stresses of navigating our cosmic neighborhood. The ancient wanderer was being tested in ways it had never experienced during its billion-year journey through interstellar space, and the outcome remained far from certain. Part 10. Controlled or autonomous? In July 2025, as the world's attention focused on the newly discovered interstellar visitor, a team of researchers published a speculative paper that would ignite imaginations and generate headlines around the globe. The RxIV preprint, authored by Abraham Loeb and colleagues, presented what they called a pedagogical thought experiment, the possibility that 3I-ATLAS might not be a natural comet at all, but rather an artificially constructed object, potentially even hostile in intent. The suggestion wasn't entirely unprecedented. Loeb had previously proposed that Oumuamua might represent alien technology, pointing to its unusual acceleration and lack of observable outgassing as potential evidence of artificial construction. But Atlas presented a different puzzle. It was clearly active, developing the coma and tail expected of natural comets, yet its trajectory and timing seemed almost suspiciously convenient for detailed study. The paper's language was carefully hedged with scientific caution, presenting the alien hypothesis as one possibility among many rather than a definitive conclusion. But in the media ecosystem of 2025, nuanced academic speculation quickly transformed into sensational headlines. Tabloid coverage and opinion pieces escalated the language far beyond what the original researchers had proposed, creating a feedback loop of increasingly dramatic claims. The mainstream scientific response was swift and measured. NASA continued to classify Atlas as a natural comet, pointing to early spectroscopic observations that showed normal cometary volatiles, albeit in unusual ratios. The James Webb Space Telescope's detection of carbon dioxide and water vapor matched expectations for natural sublimation processes, even if the specific chemistry differed from typical solar system objects. More importantly, none of the observational signatures that would indicate artificial construction had been detected. Searches for radio emissions at frequencies commonly used for communication found only natural thermal radiation. The object's light curve showed variations consistent with an irregularly shaped, rotating nucleus rather than the stable brightness expected from a constructed sphere or cylinder. No evidence of controlled acceleration beyond what could be explained by normal outgassing had been observed. The timing arguments that excited public speculation proved less compelling under closer analysis. While Atlas's near-ecliptic trajectory did bring it through the most scientifically interesting regions of our solar system, orbital mechanics shows that any object entering from interstellar space has only limited possible paths. The apparent coincidence of optimal positioning might simply reflect the fact that we're most likely to detect and study objects that pass through regions where our telescopes can observe them effectively. The Mars encounter distance of 0.19 astronomical units, often cited as suspiciously convenient for observation, actually represents a fairly typical close approach for objects on hyperbolic trajectories. Random orbital mechanics produces such encounters regularly, and the fact that we have spacecraft at Mars to take advantage of the opportunity reflects human planning rather than alien intent. SETI researchers, while maintaining appropriate skepticism about the alien hypothesis, saw the speculation as an opportunity to conduct passive monitoring campaigns during key phases of Atlas's journey. Radio telescopes around the world scheduled opportunistic observations during the Mars flyby and solar approach, listening for any signals that might indicate artificial origin. The absence of detectable transmissions, while not ruling out technological construction, failed to provide supporting evidence for the hypothesis. The search for mini-probes or deployed objects, suggested in some media coverage, found no observational support. High-resolution imaging campaigns detected no separate objects traveling alongside ATLAS, no evidence of material being deliberately released, and no structured patterns in the coma or tail that might indicate technological components. Perhaps most significantly, the chemical signatures emerging from spectroscopic analysis matched expectations for natural materials formed under alien stellar conditions. The carbon dioxide-rich composition, while unusual for solar system comets, fit models for objects formed in the outer regions of protoplanetary disks around different types of stars. The isotope ratios, when measurable, showed values consistent with natural nucleosynthesis processes rather than the artificial isotope signatures that might result from technological construction. The speculation did serve to highlight important questions about how the scientific community should respond to genuinely anomalous observations. The unusual properties of both Oumuamua and ATLAS demonstrated that interstellar visitors could exhibit behaviors outside the range of local experience, making it crucial to distinguish between naturally exotic phenomena and potentially artificial signatures. Media literacy became a critical factor in public understanding of the speculation. The progression from tentative academic hypothesis to sensational headlines illustrated how scientific uncertainty can be amplified and distorted in public discourse. The original researchers' careful hedging and emphasis on pedagogical value was often lost in coverage that presented the alien hypothesis as a serious scientific claim rather than a thought experiment. Cultural factors also played a role in the speculation's reception. The previous debates about Oumuamua had primed public audiences to view interstellar visitors as potentially mysterious or artificial. Science fiction narratives about alien probes and first contact scenarios provided ready-made frameworks for interpreting unusual astronomical discoveries. The genuine scientific excitement about Atlas's unique properties could easily be reframed as evidence for more exotic explanations. The ethical implications of such speculation deserved consideration. If genuine evidence for artificial construction were ever detected, questions of disclosure, international coordination, and public communication would become critical. The ATLAS speculation provided a useful rehearsal for how the scientific community might handle truly anomalous discoveries in the future. But for the object racing through the asteroid belt in late 2025, the alien hypothesis remained unsupported by observational evidence. The unusual chemistry that made ATLAS scientifically fascinating was better explained by natural processes operating under foreign stellar conditions than by technological construction. The trajectory that brought it through our most observable regions reflected the mathematics of orbital mechanics rather than intelligent navigation. The speculation had served its purpose as a thought experiment, generating public interest and highlighting the remarkable nature of interstellar visitors. But as ATLAS continued its journey towards solar encounter, the evidence pointed overwhelmingly toward a natural origin. An ancient comet formed around another star, carrying samples of alien chemistry that were precious precisely because they were natural products of cosmic evolution. The real mystery wasn't whether ATLAS was artificial, but how natural processes in other stellar systems could produce objects so different from our local experience. That mystery was worth pursuing with the same intensity once directed towards speculation about alien construction, and the answers would prove just as fascinating as any science fiction scenario. As ATLAS approached its closest solar encounter, the question wasn't whether it was controlled or autonomous. It was whether this natural marvel would survive long enough to reveal all the secrets of its alien chemistry and ancient history. Part 11. If Destroyed, a Shattered Visitor. The scenario unfolds gradually, almost imperceptibly at first, as thermal stresses and internal pressures build within Atlas's ancient nucleus. What begins as subtle brightness variations and asymmetric jets evolves into something more dramatic: the slow-motion disintegration of an interstellar visitor that has survived billions of years only to succumb to the intense environment of our inner solar system. The physics of cometary fragmentation is both violent and strangely beautiful. As solar heating penetrates deeper into the nucleus, volatile materials trapped within the ice-rock matrix begin sublimating rapidly, creating internal pressure that seeks release through the path of least resistance. Cracks that formed during eons of thermal cycling in interstellar space become the focal points for explosive outgassing events that can literally blow the nucleus apart. The visual progression would be unmistakable to experienced comet observers. First, the central condensation, the bright core that represents reflected sunlight from the solid nucleus, begins to elongate and develop multiple bright spots. High-resolution imaging reveals that what was once a single object is becoming several, each following slightly different trajectories as they separate under the influence of rotational forces and asymmetric outgassing. Within days or weeks of initial fragmentation, the brightness behavior changes dramatically. Instead of the steady increase expected from normal solar heating, Atlas exhibits rapid brightening followed by equally rapid fading as each fragment exhausts its surface volatiles and then becomes inactive. The overall coma expands and becomes more diffuse, losing the sharp central condensation that characterizes an intact nucleus. The tail structure responds immediately to fragmentation, developing multiple components as different fragments contribute their own gas and dust streams. What was once a coherent plasma tail becomes a complex, braided structure reflecting the multiple ion sources now distributed along the comet's orbit. The dust tail, no longer fed by a single point source, spreads into a broad fan that can extend across significant portions of the sky. For Earth-based observers, a fragmenting Atlas would create both spectacular viewing opportunities and profound scientific disappointment. The increased surface area from multiple fragments often leads to enhanced brightness that can make comets visible to the naked eye, even at considerable distances. But the same fragmentation process that creates this temporary spectacle also destroys the pristine interior materials that represent our only samples of interstellar chemistry. The meteor shower question inevitably arises whenever comet fragmentation occurs, but Atlas's geometry provides reassuring answers. The fragments would continue following the same hyperbolic trajectory as the original object, racing away from the Sun on paths that never intersect Earth's orbit. Unlike periodic comets that can deposit debris streams in Earth-crossing orbits, interstellar visitors carry their fragments away from our neighborhood entirely. The dust and gas released by fragmentation could create more subtle effects. Enhanced zodiacal light, the faint glow caused by sunlight reflecting off interplanetary dust, might show temporary increases in regions where Atlas debris concentrates. Radio observations might detect brief enhancements in plasma wave activity as the expanded ion cloud interacts more vigorously with the solar wind. But these effects would be localized and temporary, posing no threat to Earth or its technological systems. From a planetary dynamics perspective, Atlas fragmentation would be essentially irrelevant. The total mass involved, probably less than a few trillion tons, represents a negligible perturbation compared to the gravitational influences that shape planetary orbits. Even if every fragment somehow concentrated in one location, the gravitational effects would be too small to measure with our most sensitive instruments. The scientific value of fragmentation presents a complex trade-off. On one hand, breakup destroys the structural integrity that preserves layered composition and formation history within the nucleus. The gradual mixing and dispersal of interior materials makes it impossible to determine their original distribution or the sequence of accretion processes that built the comet during its formation around another star. On the other hand, fragmentation provides access to interior materials that would otherwise remain hidden beneath radiation-processed surface layers. Fresh fracture surfaces expose previously buried ices to spectroscopic analysis, potentially revealing chemical signatures that were invisible when locked within the intact nucleus. The expanding debris cloud creates a larger target for telescopic observation, making it easier to detect trace species and isotope ratios. The comparative studies with Comet ISON and C/2019 Y4-ATLAS provide frameworks for understanding how fragmentation progresses and what observational signatures to expect. Both objects showed similar patterns: initial brightening as surface area increased, followed by rapid fading as small fragments exhausted their volatile content. The debris clouds dispersed over periods of months to years, gradually becoming undetectable as they spread along extended orbital paths. High-resolution imaging would be crucial for documenting the fragmentation process and determining whether it results from internal stress, external impacts, or some combination of factors. The Hubble Space Telescope's previous observations of fragmenting comets have provided detailed views of nucleus breakup, revealing how individual pieces separate and evolve independently over time. The European Space Agency's future Comet Interceptor mission, currently planned for launch in the late 2020s, was originally designed to study pristine comet nuclei from close range. If ATLAS were to fragment, the scattered debris might actually provide multiple targets for such missions, each representing different aspects of the original object's composition and structure. Perhaps most poignantly, ATLAS fragmentation would represent the end of a story that began when our galaxy was younger and very different from its current state. An object that had wandered between the stars for billions of years, surviving cosmic ray bombardment, gravitational encounters, and the harsh environment of interstellar space, would succumb not to some dramatic cosmic catastrophe, but to the gentle warming of our familiar Sunday. The emotional resonance of such an outcome shouldn't be underestimated. Comets have always represented impermanence in human consciousness, beautiful visitors that appear briefly before fading away forever. An interstellar comet carries this symbolism to cosmic scales, embodying the vast timescales and distances that separate us from other stellar systems. Its destruction would be a reminder that even billion-year journeys can end in moments of geological time. Yet, even in destruction, ATLAS would continue contributing to science. The dispersing fragments would carry isotope signatures and chemical tracers into the outer solar system, where future missions might encounter and analyze them decades or centuries hence. The observational data from fragmentation would inform models of comet structure and composition that would improve our understanding of similar objects for generations. The possibility of destruction was real, supported by historical precedent and the mounting evidence of internal stress revealed by ATLAS's erratic brightness behavior. But destruction wouldn't mean failure. It would simply represent a different kind of scientific revelation, one that traded long-term preservation for immediate access to materials that had been hidden since our galaxy's youth. As ATLAS continued racing toward its October solar encounter, the fragmentation scenario remained one possible outcome among many. The ancient wanderer might yet prove resilient enough to survive thermal stress and emerge intact on the far side of perihelion. But if it didn't, if the stresses of solar encounter proved too much for billion-year-old ice and rock, then we would witness the spectacular end of an interstellar journey that began when the universe itself was barely half its current age. Either way, ATLAS would teach us something profound about the nature of materials formed around other stars, the physics of objects that bridge stellar systems, and our own place in a galaxy filled with wandering worlds we're only beginning to discover. Part 12. If redirected, a new orbit. The fantasy has captured imaginations since the first interstellar visitor was detected. Could a chance gravitational encounter redirect ATLAS away from its hyperbolic trajectory, trapping it permanently within our solar system? The scenario appeals to our deepest desires for cosmic companionship, the possibility that this ancient wanderer might abandon its billion-year journey to take up permanent residence among our familiar planets. The mathematics, however, tell a different story entirely. ATLAS carries a hyperbolic excess velocity of approximately 58 kilometers per second, representing kinetic energy far beyond what any solar system encounter could neutralize. To understand the scale involved, consider that even Jupiter, by far our most massive planet, can only alter an object's velocity by about 2 kilometers per second during a close flyby. Against Atlas's enormous hyperbolic energy, such perturbations are negligible corrections rather than fundamental redirections. Gravitational capture requires what orbital mechanicians call a deep encounter, a close approach that allows a massive object to bend the incoming trajectory through large angles while simultaneously bleeding off excess energy through tidal interactions or other dissipative processes. For Atlas, even the closest planetary approach occurs at Mars, where the flyby distance of 0.19 astronomical units represents a distant encounter by capture standards. The energy scales involved make permanent capture essentially impossible through gravitational means alone. Atlas would need to lose more than 99% of its kinetic energy to transition from a hyperbolic orbit to an elliptical one bound to the Sunday. No combination of planetary encounters in our solar system could achieve such dramatic energy loss, particularly given the object's retrograde trajectory that minimizes rather than maximizes gravitational assists. But subtle redirections are indeed possible and potentially observable. Mars could alter Atlas's trajectory by small amounts, changing the precise timing of solar approach or slightly modifying the departure angle. Venus, at 0.65 astronomical units in November, might provide additional minor perturbations. The cumulative effect of these encounters could shift Atlas's ultimate exit trajectory by measurable amounts without fundamentally changing its hyperbolic nature. More intriguingly, non-gravitational forces could play a role in trajectory modification. The asymmetric outgassing that creates comet tails also generates small but persistent accelerations that can accumulate over time. If Atlas develops strong, directionally biased jets during its solar approach, these forces could act like tiny rocket engines, nudging the trajectory in ways that complement gravitational perturbations. The Rosetta mission documented how outgassing forces can significantly alter comet orbits over multiple perihelion passages. For 67P/Churyumov-Gerasimenko, asymmetric jets change the orbital period by several minutes per orbit, small effects that accumulate into major changes over thousands of years. Atlas, with its unusual carbon dioxide-rich chemistry, might experience outgassing patterns different from typical water-dominated comets. However, even dramatic non-gravitational accelerations couldn't overcome Atlas's fundamental hyperbolic nature. The object carries too much energy for capture, regardless of how its trajectory might be modified by outgassing effects. Any redirection would simply change which direction it exits our solar system rather than preventing departure entirely. The concept of hiding in the belt presents another intriguing but ultimately impossible scenario. Some speculative scenarios have suggested that Atlas might somehow become trapped among the asteroid belt objects, disguising itself as a local resident while secretly maintaining its interstellar origin. The orbital mechanics make this fantasy impossible. Hyperbolic trajectories don't permit closed orbits around the Sun, regardless of where they might pass through the solar system. Post-perihelion observations will be crucial for documenting any trajectory modifications that do occur. Atlas is scheduled to reappear from solar conjunction in early December 2025, providing opportunities to measure any changes in its orbit resulting from solar encounter and planetary perturbations. These measurements will help refine models of non-gravitational forces and improve predictions for future interstellar visitors. The observational opportunities extend well beyond simple trajectory tracking. Multiple spacecraft throughout the inner solar system might catch glimpses of Atlas during different phases of its journey, providing parallax measurements that improve orbital determinations and reveal subtle perturbations. The Mars encounter on October 3rd represents a particularly valuable opportunity for spacecraft in orbit around the Red Planet. NASA's Mars Reconnaissance Orbiter, MAVEN, and the European Space Agency's Mars Express, along with surface-based assets like the Perseverance rover, All carry instruments capable of detecting bright comets under favorable circumstances. While the logistics of coordinating such observations are complex, the potential scientific return could justify the effort required to schedule special observations. The trajectory modifications, however small, carry implications for broader questions about interstellar object populations and their interactions with planetary systems. Understanding how solar system encounters alter the paths of visiting objects helps astronomers model the long-term evolution of interstellar populations and predict detection rates for future surveys. Perhaps most importantly, careful trajectory monitoring provides tests of our understanding of non-gravitational forces and plasma interactions. If ATLAS's departure trajectory differs from gravitational predictions by measurable amounts, those differences can be attributed to outgassing forces, radiation pressure effects, or electromagnetic interactions with the solar wind. Each measurement refines our knowledge of how interstellar materials respond to stellar environments. The ultimate fate remains clear. ATLAS will depart our solar system on a modified but still hyperbolic trajectory, carrying its samples of alien chemistry back into interstellar space. The precise direction of departure and the exact timing of solar system exit might be altered by solar encounter, but the fundamental outcome, a return to the galactic wilderness, cannot be changed by any realistic combination of gravitational and non-gravitational forces. This certainty brings both disappointment and relief. The disappointment comes from our inability to retain this remarkable visitor for extended study. The relief comes from the knowledge that ATLAS will continue its cosmic journey, potentially carrying samples of our solar system's environment to other stellar neighborhoods billions of years in the future. In a sense, ATLAS represents a cosmic ambassador, sampling conditions around different stars and spreading materials between stellar systems on timescales comparable to galactic evolution. Its brief visit to our neighborhood is just one episode in a story that spans galactic history, connecting stellar systems across space and time in ways that dwarf human comprehension. The redirection scenarios, however appealing to our imagination, cannot overcome the fundamental physics of interstellar trajectories. ATLAS will remain a visitor, not a permanent resident, departing our solar system with slightly modified momentum but undiminished mystery. The brief encounter will leave us with data, memories, and questions that will outlast our own civilization's ability to remember this ancient wanderer from the stars. Part 13. The Alien Hypothesis Expanded. The speculation that began with a single ArXiv preprint in July 2025 had evolved into something far more complex and contentious by the time ATLAS reached its asteroid belt crossing. What started as an academic thought experiment, could this interstellar visitor represent alien technology, had morphed through media amplification and public imagination into claims that seemed to take on lives of their own. Abraham Loeb and his colleagues had carefully framed their original paper as pedagogical, using phrases like possibly hostile, not as definitive claims, but as extreme examples designed to illustrate how extraordinary evidence would be required to support extraordinary hypotheses. The scientific method demands that all possibilities be considered, even unlikely ones, provided they generate testable predictions that can distinguish between competing explanations. But the progression from scientific speculation to public narrative illustrated how extraordinary claims can outpace the evidence that supports them. Social media algorithms, designed to promote engagement rather than accuracy, amplified the most sensational interpretations while often omitting the careful hedging and uncertainty quantification that characterized the original research. The scientific community's response remained measured and evidence-based. NASA's official position classified ATLAS as a natural comet based on multiple lines of observational evidence. The spectroscopic signatures detected by the James Webb Space Telescope and ground-based observatories matched expectations for natural sublimation processes, even if the specific chemistry differed from typical solar system objects. More critically, none of the smoking gun signatures that would indicate artificial construction had been detected, despite intensive monitoring by multiple facilities. Radio surveys found no coherent transmissions at frequencies commonly used for communication or navigation. Optical monitoring revealed no evidence of controlled acceleration beyond what could be explained by normal outgassing processes. High-resolution imaging showed no geometric structures or surface features incompatible with natural formation. The burden of proof for extraordinary claims requires extraordinary evidence, and such evidence simply hadn't materialized despite months of detailed observations. The alien hypothesis remained possible in the abstract sense that most unfalsifiable propositions remain possible, but it lacked the observational support that would elevate it from speculation to serious scientific consideration. SETI researchers, while maintaining appropriate scientific skepticism, had embraced the opportunity to conduct passive monitoring campaigns during key phases of ATLAS's journey. The Breakthrough Listen project and other radio survey initiatives scheduled dedicated observation time around critical dates, the Mars encounter, solar approach, and departure phases when any hypothetical technology might be most likely to activate or communicate. The absence of detectable signals, while not definitively ruling out technological origin, failed to provide the positive evidence that would be required to support such claims. In science, negative results carry weight. They constrain the parameter space of possible explanations and eliminate hypotheses that make specific, testable predictions. The search for deployed objects, or mini-probes, had similarly yielded negative results. Multiple high-resolution imaging campaigns, including observations by the Hubble Space Telescope and ground-based adaptive optics systems, detected no separate objects traveling alongside ATLAS, no evidence of structured material release, and no geometric patterns in the coma or tail that might indicate technological components. Perhaps most significantly, the isotopic signatures emerging from detailed spectroscopic analysis matched expectations for natural materials formed through stellar nucleosynthesis processes. The carbon, oxygen, and hydrogen isotope ratios, when measurable, fell within ranges predicted for objects formed in different galactic environments, rather than showing the artificial signatures that might result from technological construction or propulsion systems. The cultural context surrounding these speculations deserved analysis in its own right. The previous debates about Oumuamua had established interstellar visitors as potentially mysterious objects worthy of exotic explanations. Science fiction narratives about alien probes, first contact scenarios, and hidden technological surveillance provided ready-made interpretive frameworks that could be applied to any unusual astronomical discovery. Media coverage often emphasized the most sensational possibilities, while downplaying the careful uncertainty quantification that characterizes responsible scientific communication. Headlines that proclaimed, "Scientists say comet could be alien probe," rarely conveyed the conditional language, probability assessments, and alternative explanations that appeared in the original research papers. The phenomenon highlighted important questions about science communication in an era of rapid information dissemination and algorithmic amplification. How should researchers balance legitimate scientific speculation with public understanding? What responsibilities do scientists have when their hypotheses are misrepresented or sensationalized in popular media? Educational opportunities emerged from the controversy. The alien speculation provided teachable moments about the scientific method, the nature of evidence, and the process by which extraordinary claims are evaluated within the scientific community. The progression from hypothesis to testing to conclusion offered clear examples of how science distinguishes between speculation and established knowledge. The ethical implications of such speculation also warranted consideration. If genuine evidence for artificial construction were ever detected, questions of disclosure, international coordination, and public communication would become critical. The ATLAS controversy provided a useful case study for how the scientific community might handle truly anomalous discoveries in future encounters. But perhaps most importantly, the alien speculation had served to highlight just how remarkable ATLAS was as a natural object. The unusual chemistry, the convenient trajectory, the timing of discovery. All the factors that made technological origins seem plausible were actually evidence for the incredible diversity of natural processes operating throughout our galaxy. The carbon dioxide-rich composition revealed formation conditions unlike anything in our local stellar neighborhood. The near-ecliptic trajectory demonstrated that interstellar space contains objects following every conceivable orbital geometry. The detection timing reflected our improving ability to discover and characterize objects that would have remained invisible to previous generations of telescopes. In a very real sense, ATLAS was far more interesting as a natural phenomenon than it would have been as alien technology. Technological objects, however advanced, operate within constraints imposed by physics, engineering, and presumed rational purposes. Natural objects, shaped by processes we don't fully understand operating under conditions we can barely imagine, can exhibit behaviors that transcend our current theoretical frameworks. The real mystery wasn't whether ATLAS was controlled by alien intelligence, but how natural processes in foreign stellar environments could produce objects so different from our local experience. That mystery was worth pursuing with the same intensity once directed towards speculation about technological construction, and the answers would prove just as profound as any first contact scenario. As ATLAS continued its journey through the asteroid belt, the evidence pointed overwhelmingly toward a natural origin, not because aliens were impossible, but because the natural universe was strange enough to explain everything we were observing. The cosmos didn't need artificial enhancement to generate objects that challenged our understanding and fired our imagination. The alien hypothesis had done its job, encouraging rigorous observation and analysis while generating public interest in interstellar visitors. But the natural explanation emerging from that analysis was proving far more fascinating than any science fiction alternative. ATLAS was teaching us that reality, when viewed on cosmic scales, could be more exotic than our wildest speculations about alien technology. Part 14. The Wake Up Call. The detection of ATLAS represented more than just another astronomical discovery. It was a preview of our future, a glimpse into an era when interstellar visitors might become routine rather than extraordinary. Our current sky surveys, impressive as they seem to contemporary observers, capture only a tiny fraction of the objects passing through our cosmic neighborhood at any given time. The catalogues maintained by NASA, ESA, and ground-based survey programs contain millions of known objects, from near-Earth asteroids to distant Kuiper Belt residents. But these databases, comprehensive as they appear, represent primarily objects that belong to our solar system, permanent residents bound by the Sun's gravity and following predictable orbits that can be calculated centuries into the future. Interstellar visitors present entirely different challenges. They appear without warning from random directions, follow hyperbolic trajectories that carry them quickly through our detection zones, and often remain visible for only weeks or months before fading beyond instrumental limits. The discovery of ATLAS, like its predecessors, Oumuamua and Borisov, depended as much on luck and timing as on systematic search strategies. This situation is about to change dramatically with the completion of the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope. Beginning operations in the mid-2020s, this revolutionary facility will conduct a decade-long survey of the southern sky, imaging the entire visible universe every few nights with unprecedented depth and precision. Current estimates for interstellar object detection rates vary widely depending on assumptions about size distributions, approach geometries, and instrumental sensitivity limits. Conservative projections suggest the Rubin Observatory might detect 1 to 2 interstellar visitors per year, a tenfold increase over current discovery rates. More optimistic scenarios, based on theoretical models of galactic object populations, predict dozens of detections annually once the survey reaches full operational capability. The implications of such discovery rates extend far beyond simple object catalogues. Each interstellar visitor carries unique chemical signatures and formation histories from different stellar environments. Systematic studies of multiple objects would reveal patterns and correlations impossible to detect from individual cases like ATLAS. Statistical analysis of interstellar populations could constrain models of planetary formation, stellar evolution, and galactic chemical evolution. But increased discovery rates also create new challenges for rapid response observation and characterization. ATLAS benefited from months of advance warning and coordinated observational campaigns involving multiple facilities worldwide. If interstellar visitors become numerous enough, the astronomical community will need automated detection algorithms, pre-planned response protocols, and flexible scheduling systems that can adapt to unexpected discoveries. The ATLAS experience has provided valuable lessons for managing future interstellar encounters. The coordination between NASA, ESA, NOILAB, and international partners demonstrated how effectively the global astronomical community can mobilize resources when presented with rare opportunities. The rapid deployment of space-based assets, like the James Webb Space Telescope and Hubble, showed the value of flexible scheduling and priority override capabilities. Perhaps most importantly, ATLAS has served as a dress rehearsal for public communication and media management during high-profile astronomical events. The progression from technical discovery announcements to widespread public interest to sensationalized speculation illustrated both the opportunities and challenges associated with communicating cutting-edge science to general audiences. The planetary defense angle adds another layer of complexity to interstellar object detection and characterization. While ATLAS posed no threat to Earth, future visitors might follow trajectories that bring them closer to our planet or its orbital path. Distinguishing between harmless interstellar visitors and potentially hazardous objects requires rapid orbit determination and accurate size estimation, capabilities that current survey systems are still developing. The technical infrastructure for handling increased detection rates is gradually taking shape. Machine learning algorithms can now identify moving objects in survey data with accuracy approaching that of human analysts. Automated follow-up systems can trigger spectroscopic observations at multiple facilities based on predefined criteria. Communication networks can disseminate discovery information to the global astronomical community within hours of detection. Educational opportunities multiply as interstellar visitors become more common. Each new discovery provides fresh examples for discussing stellar formation, planetary dynamics, and the chemical evolution of galaxies. The diversity of objects, some resembling familiar solar system bodies, others exhibiting completely alien properties, offers natural laboratories for comparative planetology on interstellar scales. The data archival and analysis challenges are equally significant. Each well-observed interstellar visitor generates terabytes of imaging, spectroscopic, and photometric data that must be processed, archived, and made available for future research. The ATLAS dataset, accumulated over months of intensive observations, will serve as a reference standard for comparing future discoveries and testing theoretical models. International cooperation becomes even more critical as detection rates increase. No single nation or observatory system can comprehensively characterize multiple simultaneous interstellar visitors. Sharing telescope time, coordinating observations, and pooling analytical expertise require agreements and protocols that transcend traditional institutional boundaries. The technological implications extend beyond astronomy into spacecraft design and mission planning. If interstellar visitors prove common enough, dedicated interceptor missions become feasible, spacecraft stationed at strategic locations within the solar system, ready for rapid deployment to rendezvous with newly discovered objects. Conceptual studies for such missions already exist in the literature, awaiting sufficient detection rates to justify their development. Amateur astronomers will play increasingly important roles in interstellar visitor detection and monitoring. Modern CCD cameras and computerized telescopes have democratized astronomical observation to an extent unimaginable just decades ago. Distributed networks of amateur observers can provide continuous monitoring that professional facilities, with their competing priorities and limited telescope time, cannot match. The wake-up call represented by ATLAS extends beyond technical preparedness to philosophical readiness. As interstellar visitors become routine, human perspective on our place in the galaxy will inevitably shift. We are not isolated residents of a unique stellar system, but participants in a vast galactic ecosystem where materials, and possibly life itself, migrate between stars on timescales measured in millions and billions of years. Each interstellar visitor represents a cosmic messenger, carrying samples of chemistry and physics from stellar environments we may never visit directly. The accumulated data from dozens or hundreds of such objects will provide insights into galactic evolution, planetary formation processes, and the distribution of organic materials throughout our local region of the Milky Way. The preparedness isn't just about defense or scientific opportunity. It's about recognizing our membership in a much larger cosmic community. The materials in our own bodies, forged in stellar cores and dispersed by supernovae, share common origins with the substances traveling between stars aboard objects like ATLAS. We are studying not alien chemistry, but distant relatives in the vast family of cosmic materials. As ATLAS continues its passage towards solar encounter, it carries with it the hopes and preparations of an astronomical community learning to expect the unexpected. The ancient wanderer has already taught us that our cosmic neighborhood is far more dynamic and interconnected than previous generations ever imagined. The visitors yet to come will complete that education, transforming interstellar objects from rare curiosities into familiar representatives of our galactic heritage. The wake-up call has sounded. The era of routine interstellar visitor encounters is beginning, and ATLAS has shown us both the opportunities and challenges that await in our expanding cosmic awareness. Part 15. Conclusion. The Cosmic Mirror. As ATLAS races through the final phases of its asteroid belt crossing, preparing for its October encounter with our Sun, it carries with it more than just ancient ice and alien chemistry. This wanderer from the galactic depths has become a mirror in which we see reflected our own place in a universe far stranger and more interconnected than previous generations could have imagined. Whether ATLAS survives its solar encounter intact, gradually disintegrates under thermal stress, or fragments spectacularly across our skies, it has already fulfilled its most important function as cosmic messenger. Every spectrum, every brightness measurement, every morphological detail captured by our telescopes adds to a growing understanding of how materials circulate between stellar systems, carrying with them the chemical signatures of distant worlds. The retrograde trajectory that threads ATLAS directly through our solar system's most populated regions serves as a reminder that cosmic traffic flows in all directions, following paths determined by gravitational dynamics that operate on galactic scales. The same orbital mechanics that govern planetary motion around our Sun shape the wandering paths of objects scattered between the stars, creating encounters like this, one that bridge stellar neighborhoods separated by light years of space. ATLAS's unusual chemistry, that carbon dioxide-rich signature detected by the James Webb Space Telescope, provides a tantalizing glimpse into formation conditions around stars very different from our own. The ratios of volatiles, the isotopic signatures, the physical properties all speak to protoplanetary environments where temperature gradients, radiation fields, and chemical abundances created objects, unlike anything in our local experience. There is profound beauty in this ordinariness made extraordinary by distance and time. ATLAS isn't miraculous or supernatural. It's a natural product of stellar formation processes operating under slightly different conditions than those that shaped our own solar system. Yet those subtle differences, magnified by billions of years of evolution, have created an object that challenges our understanding of planetary formation and chemical evolution throughout the galaxy. The philosophical implications extend beyond scientific discovery into questions of cosmic perspective and human significance. We are observers of processes that began when our galaxy was younger and very different from its current state. The materials now sublimating from Atlas's nucleus were incorporated into solid form when entire generations of stars were being born and dying in stellar nurseries we can barely detect with our most powerful telescopes. Each photon of reflected sunlight, each spectral line revealing molecular composition, connects us directly to conditions that existed billions of years before our own planet formed. We are literally looking backward in time, not through telescopic observation of distant light sources, but through direct analysis of materials that have preserved the chemical signatures of ancient galactic environments. The technical achievements represented by ATLAS observations demonstrate how far human capability has advanced in understanding our cosmic environment. The coordination between space-based telescopes, ground-based observatories, and theoretical models has created an analytical framework that can extract detailed information from objects moving at hypervelocity through our solar system. We have become cosmic archaeologists, reading formation histories from materials that predate our existence by billions of years. Yet the encounter also highlights the vast scales of ignorance that still surround us. ATLAS represents just one sample from the Milky Way's thick disk population, one data point in a distribution that contains billions of similar objects following their own wandering paths through interstellar space. The diversity of chemistry, composition, and formation history represented by the full population remains almost entirely unknown. The practical implications for future discoveries are equally profound. ATLAS has served as a preview of the era that awaits when the Vera C. Rubin Observatory begins detecting interstellar visitors routinely rather than accidentally. The techniques developed for rapid characterization, the international coordination protocols, the public communication strategies, all are dress rehearsals for managing a future where interstellar visitors become familiar rather than extraordinary. The safety questions that inevitably accompany any discussion of incoming cosmic objects have been definitively answered for ATLAS. The closest Earth approach of 1.8 astronomical units places it well beyond any possibility of direct interaction with our planet. Even complete fragmentation would produce debris following the same hyperbolic trajectory, carrying all fragments away from Earth rather than toward it. This safety provides the luxury of pure scientific appreciation, free from the anxiety that accompanies potentially hazardous objects. ATLAS can be studied for what it teaches us about galactic evolution, planetary formation, and interstellar chemistry, without the overlay of threat assessment that characterizes near-Earth object research. The cultural impact of ATLAS extends beyond scientific literature into broader human consciousness of our place in cosmic time and space. The realization that our solar system receives regular visits from objects formed around other stars fundamentally changes perspective on isolation and connectivity. We are not alone in the sense that fictional narratives often imagine, but we are connected through material processes that operate on scales both intimate and vast. The dust that ATLAS sheds as it approaches our Sun will join the zodiacal cloud that fills interplanetary space, mixing interstellar materials with the debris from solar system formation. Future spacecraft and perhaps future human explorers will encounter these particles without knowing their extraordinary origin. Interstellar chemistry will become part of our local environment, indistinguishable from materials that never left our stellar neighborhood. In this sense, ATLAS represents both arrival and departure, visitation and integration. The object itself will race away from our Sun on a modified but still hyperbolic trajectory, carrying samples of our solar wind environment back into the galactic wilderness. But the materials it leaves behind, the gases and dust that form its coma and tail, will remain with us, permanent additions to our local cosmic environment. The observational campaign continues as ATLAS approaches solar encounter, but the most important discoveries have already been made. We have confirmed that interstellar space contains a diverse population of objects carrying chemistry from throughout our galaxy's history. We have demonstrated that natural processes in foreign stellar environments can produce materials with properties that challenge our theoretical understanding. Most importantly, we have shown that our solar system is not an isolated island, but a way station in a vast network of material exchange that connects all stellar systems across cosmic time. As Atlas fades from our telescopes, whether through survival and departure or through fragmentation and dispersal, it leaves behind a transformed understanding of our place in the galactic community. We are citizens of a universe far more dynamic and interconnected than we previously imagined, participants in processes that link stellar formation throughout our region of the Milky Way. The ancient wanderer has delivered its message, written in the universal language of physics and chemistry. The translation continues, but the essential meaning is already clear. We are not alone, we have never been alone, and the materials that make up our world participate in exchanges that span the galaxy and bridge eons of cosmic time. The cosmic mirror reflects not isolation but connection, not uniqueness, but participation in processes that extend from our local neighborhood to the most distant stars visible in our night sky. Atlas has shown us our reflection in that mirror, and the face looking back is both familiar and wondrously strange, ancient and eternal, local and cosmic. The next visitor is already on its way, carrying fresh messages from stellar systems we will never see directly. The conversation continues, written in the eternal language of wandering worlds.